Alright, so what I'm going to do is an intro to Chapter 9, which is bonding, chemical bonding, so we're going to go over some stuff. Happy Halloween, by the way. Here's a little jack-o'-lantern. Not really. Alright, here we go. So, intro to bonding. Chemical bond is an attractive force that holds two or more atoms together. Falls into three categories. You have a covalent bond, which is between nonmetal and a nonmetal. That's the definition you learned last year in honors chemistry. An ionic bond is between a metal and a nonmetal and is a transfer of electrons. Covalent bond is a sharing of electrons. And finally, metallic bond we'll deal with in Chapter 11, so you don't have to worry about it right now. Here's an example of an ionic bond. You have two ions. You have a sodium and a chloride ion. It's a transfer of electron from sodium to chloride. That's what provides a positive charge for sodium and a negative charge for chlorine. Ionic compounds are made of what are called crystal lattices because the atoms, or excuse me, ions stack in a repeating pattern with each other. Covalent bonding is between two nonmetals, so it's a nonmetal and nonmetal. It's basically a bond or shared, so you have a nucleus here, and you have a shared pair of electrons if it's a single bond, or it could be a double or a triple. Definitions you need to be aware of. First definition, we talked about this in the last chapter, is electronegativity. Electronegativity is the attraction an atom has for electrons in a chemical bond. So that's really what you're talking about, is how strongly do they pull in a bond. Polar bond is where there's a difference. Different electronegativities, and we're going to get to how you figure that out. Basically, one atom pulls the electrons more strongly than the other, and it creates basically a partial charge on one side, positive, and a partial negative charge on the other side. So it's an unequal sharing of electrons. So that's the same slide. Nice job. Ionic bonds, remember, metal to nonmetal, cation and anion. They involve a transfer of electrons. So one electron is given up from a metal. The electron, or more than one electron, goes to a nonmetal. We basically use the concept of electronegativity to actually classify ionic bonds, but at its fundamental, simplest, an ionic bond is between a metal and a nonmetal. Then you go to where you can figure out using electronegativity values. We say that anything that has a difference in electronegativity of about 1.7 Paulings, or you subtract the electronegativity values, then that is considered an ionic bond. So you can classify it using electronegativity values. So sodium chloride, you could say, is ionic because if you look up the value for sodium and chloride, the difference, the delta En, the difference in electronegativity, is 2.0. Copper oxide, the difference is 1.7 Paulings. Difference in electronegativity, so that's what you see there, classifies it as ionic. If you look, basically the way we're going to classify these is anything that has an electronegativity difference above 1.7 we say is an ionic bond. So anything 1.7 or greater is going to be an ionic bond. Anything that is 0.5, below 0.5, we say is going to be nonpolar covalent, which is between a nonmetal and a nonmetal. So it's nonpolar covalent. And then the third type of bond that we'll be talking about is polar covalent. A polar covalent bond means that it has an electronegativity value between 1.7 and 0.5, and it is a polar molecule. So one side is positive, one side is going to be slightly negative. So that's basically the scale we use when we look at these values. That's what you want to keep in mind. Covalent, really the start of it, you should know, is two nonmetals are bonded together. It's a sharing of electrons. We can actually figure out two different types of covalent bonds based on that. So if we look right here, a polar covalent bond is an unequal sharing of electrons, and it creates a dipole. Dipole is another name for a molecule that is polar. It has a positive and a negative end. Basically, this occurs when there's a small but significant difference in electronegativity, and really you're looking at between 0.5 and 1.7 Paulings. Example, if you took nitrogen and hydrogen, you take the two values and subtracted them, the difference is 0.9, therefore it is considered to be a polar covalent bond. The other type of covalent bond is nonpolar covalent bond. That is an equal sharing of electrons. Well, how do we say something's an equal sharing of electrons? If the electronegativity difference is below 0, or excuse me, above 0 to 0.4, means that it is considered a nonpolar covalent bond, so their electrons are shared equally, so it does not form a dipole. And remember, a dipole is a molecule that is polar. If you look here, dipole is separation of charge. A polar bond is an example of a dipole. A dipole moment, when we measure that, is the magnitude. How much of a difference is there between the two charges on one side of a molecule or the atom? It really depends on the size of the charges. And a polar molecule is one that possesses an overall dipole moment, which basically, if you look at a molecule, I'll show you, one side has a positive charge, one side does not, or a negative charge because of the electrons. F2, if you look at F2, there's 2 fluorine atoms. They have the same electronegativity, therefore the electrons in the bond here are equally shared. So if you look, the electrons are equally shared, therefore both sides, no one has an induced dipole or a polar moment. H and F. The electronegativity of F is 4.0. Hydrogen has an electronegativity of 2.1. Obviously, this is more electronegative, so the electrons are in the bond are closer to fluorine than they are to hydrogen. Therefore, we say that this has a slightly negative charge to this side and a positive charge to that side. It is considered a dipole because it has a positive side to it and a negative side to it. So it's like a magnet. A magnet's kind of polar. If you look at something that's very polar, look right here. If you look, lithium fluoride. You have lithium. Whoops. I have lithium. Try that again. I have lithium right here, Li, fluoride right there. That is an ionic bond, so it's a complete transfer of electrons. This is positive, this is negative. That is lithium fluoride. So, when we look, here's a table of electronegativities. We talked about this in the previous chapter, that if you look, basically, as you go this way in the periodic table, electronegativity increases. Fluorine is the most electronegative out of all the elements. You'll need to, in your notes that you print tonight, print out a copy of this table right here. Whoops. This table right here, which shows you the electronegativities of all the elements. They are relative values, so if you want to find a difference in electronegativity in a bond, you take each of the values from the table and you just subtract the larger one from the smaller one. So for example, lithium fluoride. I want to find out what the delta En is so I can classify it. So I go back here. Fluorine is 4.0. Lithium is 1.0. So what do? I go 4.0 minus 1.0. I get an electronegativity difference of 3.0. And on the scale, anything above a 1.7, I would consider that to be an ionic bond. Br, bromine and bromine. If I look, the value for bromine is 2.8. I come back here. This is a no-brainer. The difference in electronegativity is going to be 2.8 minus 2.8. So obviously, it's going to be 0. And if it's 0, we're going to say that bond is non-polar. Aluminum chloride. You got a metal and a non-metal, so we come over here. Chloride has a value of 3.0. Aluminum has a value of 1.5. If you look, that's very close to the borderline, but we know it's a metal and a non-metal, so we already know it's ionic. But if we did it, it was 3.0 minus 1.5, so the difference is 1.5. But we know it's ionic because it's a metal and a non-metal, so we don't really have to deal with that. It was pretty obvious. What about carbon and sulfur? If you look up carbon, the value for carbon is 2.5. Sulfur is 2.5. Right away, we know the electronegativity difference, 2.5 minus 2.5, is going to be 0, so we know it's non-polar. Last but not least, carbon and hydrogen. So if you look right here, carbon has a value of 2.5, hydrogen has a value of 2.1. So when we go back here, we do a difference in electronegativity, 2.5 minus 2.1. We're going to say this bond is a non-polar bond also, because the difference comes out to be 0.4. And if we look on that little chart I put earlier, that means it's a non-polar bond, non-polar covalent. You want to print this chart, make sure you have it in your notebook for tomorrow. Next thing, talking about chemical bonds, we have single bonds, double bonds, and triple bonds. The difference that you know, or the trend is, as bonds, the number of bonds increases, bond strength increases. So if you go from a single bond, a double bond's stronger, and a triple bond's the strongest. So the number of bonds and bond strength are directly related. Bond length is inversely related. So for example, a single bond is actually the longest. Then you go to a double bond, which is a little bit shorter, and a triple bond, which is even shorter. So the relationship between bond length and number of bonds is an inverse relationship. So as the number of bonds increases, the bond gets shorter. If you look right here, whoops, it's missing. I guess that's it. So you have a homework assignment 9.1 for homework tonight. Have a good evening. I will see you tomorrow. Bye.